good. I was going to start, but then it occurred to me that actually there is no point to teaching an empty room.
Has that's never happened, has it?
Well, at Princeton it happened.
Really?
So yeah, that's why I have this dream of giving a lecture to an empty room. But the camera kind of ruins the point. So yeah, so at Princeton there was one class taught by Professor Dork, D-W-O-R-K, in p-adic analysis. And the class had only 3 students. And apparently one day, one of the students came in maybe 15 or 20 minutes late. And she found Dork there lecturing, and he'd been lecturing to nobody for those 15 or 20 minutes. Yeah, we weren't sure if he was so focused that he did not even notice, or if he had just done it for what reason. Yeah, we weren't sure. But yeah, it has happened before. Okay. Well, in any case, you were here, so let me teach you. So let's remember what we're talking about, right? We're trying to get the L2 convergence of the Fourier series, right? L2 convergence of the Fourier series, and the way we're doing it is by using this thing that we're calling the best. The big tool is going to be this thing called the best approximation lemma. Hey, Justin. So the best approximation lemma, and this is actually a tool from linear algebra, basically. So you say, okay, so let me state it. You have f integrable on negative pi. Then over the set of trigonometric polynomials, so that is things that look like C sub n, E sub n, linear combinations of the E sub n, where the indices are all smaller in size than some finite number. Okay. Then over the set of trigonometric polynomials, S and F, right? The Fourier series, the partial sum of the Fourier series, is the best approximation. Okay. So this is what we did at the end of class last time, right? Right. Given an integrable function, then if you're looking at the trigonometric polynomials, the partial sum of the Fourier series up until that point is actually the best approximation. Okay, and we're notating this f sub n as we're also calling it a sub n. F sub n is of course the inner product of f against e sub n. Right. That's how you get the Fourier coefficients. Okay. Right. So let me just recall the proof because we're going to need certain aspects of it. So first you say, well, look, observe that if you take f and subtract off the nth partial sum, then that is orthogonal to any C sub n, E sub n, where n is less than equal to n. Right, it's orthogonal to, well, let me say it this way. It's orthogonal to any E sub n for n in absolute value less than n. Right? Is that? I hope that's pretty clear, right? You say, well, look, if we take this guy, this minus summation f e sub n, e sub n, right? and we take the inner product of it against, maybe I should say, let me use k's here, sorry. You integrate it against that e sub n, where, you know, some n is that n is in size less than n, right? Well, what's going to happen, right? What's going to happen? By linearity, we're going to get f against e sub n, right? And then we're going to get minus this against that, right? We get this against that. But this is orthogonal to everybody, right? This guy is orthogonal to everybody except for itself, right? So the only one we're going to pick off, we're going to get f e sub n, and then we're going to get e sub n against itself, right? Which is 1, right? And so we get 0. Right? So that's the first thing. This thing is orthogonal to anybody like this. And so, so if we're looking at the L2 norm, right? If we look at the L2 norm of this, squared, then we can say, well, this is, we can rewrite this as this. I'm sorry. If we look at the L2 norm of f squared, right, then we can rewrite that by the Pythagorean theorem as this squared plus this squared. Right, because this is going to be perpendicular to this, right? By what we just said, this is perpendicular to this. Right. That is to say, this plus the sum of the ANs squared times the coefficient squared. Okay, and further, actually this part is not really relevant right now. Sorry, this just take this as a side comment. So I just think if we take any linear combination of the e sub n's, okay, right. So what we're saying is that, you know, the partial sum of the Fourier series, is going to be the best approximation, right? So take some other guy and look at the difference in the L2 norm between that and your function. Okay. We can rewrite that as f minus partial sum plus the partial sum minus this c sub n guy. Right, and then we say, well, you know, by part 1, this is orthogonal to this, right? So we get that this, by Pythagorean theorem, we get that this, the norm of this thing is this squared plus the norm of this thing squared, right? But the norm of this thing squared is summation a sub n minus c sub n squared. Right, and so, you know, we said this last time, right? Like, so what does this tell you? This tells you that if you're trying to approximate in L2 the function by by linear combinations, by trigonometric polynomials of where E sub n, the indices are smaller than capital N. Well, the best thing you can do, right? The smallest error you can get is achieved when C sub n are all equal to the Fourier coefficients, right? So that's the point here. Right? Okay. So this is what we kind of rushed through at the end of class last time. Any questions about that? Okay. A couple of points. One is that this is really a linear algebra result, right? Like you could have seen this result in your linear algebra class. You start off with any orthonormal set, right? You start off with an orthonormal set, right? Here we've got these guys. We have our orthonormal set, and then you do exactly the same thing, and you'd see that the best approximation is given by something like this, right? The best approximation, and the argument is exactly the same. So one, this is really kind of this is a result that you might have seen in a linear algebra class, and two, we could do this for any orthonormal set, right? It doesn't have to be our E sub n, our characters, right? We could actually do this if we have some other set of orthonormal functions, then we can do exactly the same argument. So okay, so that's that. Okay, so now we're going to use that to get the L2 convergence. Okay, so here's the big result. In this, one of the big results in this chapter. So here it is. Let's say that f is integrable on the circle. Okay. Then the limit as n goes to infinity of 1 over 2 pi, determinant pi of f theta minus Sn f theta squared goes to 0. Okay. So in other words, this is saying that the distance between these two things in the L2, the distance in the L2 sense goes to 0. Right? You could write this Sf minus Snf L2 goes to 0. Okay, so the proof of this relies on the Weierstrass approximation theorem. Okay, what's the Weierstrass approximation theorem? Anybody remember? Yeah, go ahead, Jake.
Uniformly approximated by polynomials.
By trigonometric polynomials in this case.
Okay.
Yeah. So here, we have some function, right? So it says that if you have a continuous function on negative pi, then there exists P sub n trigonometric polynomials such that the P sub n converge uniformly to f. Okay. So we're gonna show this using kind of the standard tactic, which is first we're gonna show it for continuous functions, and then we're gonna use L1 approximation of we're gonna use that any Riemann integrable function is approximable in the L1 sense by continuous functions that have the same bound as the Riemann integrable function. Okay, so the proof goes like this. You say, well, you start off and you say, well, suppose that f is continuous, right? Then we know that there exists some some trigonometric polynomial right? We want we want to show that we can make this as small as we can make this as small as we want. So given epsilon, choose your by Weierstrass, choose your p sub n trigonometric polynomial so that the distance between p sub n and f is uniformly smaller than epsilon, right? For all theta in right? Right. But that tells you, the fact that the distance between these two guys is less than epsilon means that the L2 difference between these two guys is also less than epsilon, right? Right? Because look, the functions are within epsilon of each other. Here, if you look at the difference, how do you get the difference? You square it, you integrate it, and you take the square root, right? Right. So look, the L2 distance between these guys, right, is this Pn of this f squared, everything to the 1/2. Right, but the integrand is smaller than epsilon squared, right? So you just pull that thing out, you get epsilon. Okay, so there's a trigonometric by Weierstrass. We can choose a trigonometric polynomial, p sub n, such that this is such that the distance is smaller than epsilon, right? Okay. So we know that we can get we can get a trigonometric polynomial within epsilon of this, but we also know we also have the best approximation lemma, right? The best approximation lemma says that SNF is the best approximation of f in L2, right? So you just look at the trigonometric polynomial and see, how far out its coefficients go, right? And then you take take n large enough. So for n large enough, we know that all of the s of n's must be, the distance between s of n and f must be smaller than that, right? Must be smaller than that. Okay, so now assume f is just some integrable function. Now assume that f is integrable. Actually, before we say that, let me just comment that this business of saying that functions are conforming, for the p sub n to converge uniformly to f, right? You know, that means that, right, the supremum of the difference, the supremum of the difference, the supremum of the difference, right, goes to 0. Right? That's the same thing as uniform convergence, right? This is sort of what we call the L infinity. It's the L infinity difference, right? This is the L infinity norm of the difference of these functions. Okay, so what we're saying here is that, you know, if these guys converge in L infinity, then they're definitely going to converge in L2. Okay, just briefly, that's how one says this. This is not exactly the L infinity norm. One takes rather something called the essential supremum, where you disregard measure 0. You disregard differences on measure 0. So, like, you don't really care if the function jumps up at one point. Okay, so now we assume the function is integrable, right? We want to show that the Fourier series converges in L2, and what we do is we use the lemma. Right? So recall, we choose a continuous function g with the same bound b as f, such that the L1 norm is close, right? Such that this thing is smaller than something. Right, I think we choose it to be e squared over 2b, epsilon squared over 2b. Okay, so and now what we're going to say is that the L1 closeness of those guys ensures the L2 ensures that L2 closeness. Okay, so then we'll say, look, this guy is L2 close to that guy. That guy is L2 close to the partial sums. Right? No, that guy is L2. That guy is close to a trigonometric polynomial, right? And then we use the best approximation and say, well, look, if this guy is within is L2 close to a trigonometric polynomial, it must be even closer to its Fourier series. And in this case, we're not, it's a little bit more, it makes more sense in this case, because you're talking about the trigonometric polynomial. You're using the Fourier series of this guy, right? And you say, look, there's a trigonometric polynomial. There's a trigonometric polynomial close to this guy. That means that this guy's Fourier series must be even closer than that guy. So now we want to see that. So now consider, this. So you consider this thing, you say, and you make kind of a dumb bound, which is, you say, well, each of these guys is smaller than b, so I'm going to bound one of them by 2b. Right? So I can throw out this is less than or equal to 2b over 2 pi. Oops. Right. You just bound one of the factors by 2b. Okay. but that does it for you, right? Because then we get that this thing is smaller than epsilon squared over 2b quantity squared, which is just epsilon. Okay. So what does that tell you? That tells you that the L2 difference between these two guys is smaller than epsilon. And then you say, well, by what we just saw, we know that this G is close to some, trigonometric polynomial. As before, there exists a trigonometric polynomial. There exists a trigonometric polynomial that this guy is close to, and so, right, and so the distance between f and the trigonometric polynomial is smaller than 2 epsilon, but that tells us that the distance between f and SNF must be smaller than that by the best approximation. Okay.
Earlier we used L infinity convergence to show L square convergence, and now we're using L1 convergence to show L2 convergence.
Yes.
So are these all equivalent?
No. So I mean, yes on an interval, but when you're talking about on R, then no, because you get a functions.
But since we're working on the interval, it's all okay.
Yes. Yes.
Okay.
Yeah.
Does the interval have to be closed? Does it have to be compact?
Generally, you assume that. Generally, you assume that. Yeah. Because you want to talk about like uniform continuity and stuff like that.
I was just thinking, does the fact that all the L norms are give the same information on a compact interval, is that because the function is bounded here? So
Yeah.
it doesn't matter how many powers we're taking?
Yeah, exactly.
Okay.
Yeah. But then when you're talking about the infinite interval, then your function, well, the trouble is that when you integrate it, you're like, even if the square of your integral converges, that doesn't mean that your original integral converges.
Right. Because
So-
of things like 1 over n.
Exactly. Yeah. Okay. Okay. I hope that's clear. Okay. So we have now that the Fourier series converges in L2, and there's a bunch of consequences. Parseval's identity. So Parseval's identity says let f be an integral function, and let a sub n be the Fourier Fourier coefficients. Then the sum of the squares of the Fourier coefficients equals the L2 norm squared. Okay, so you might have seen this sort of thing in linear algebra. Now we have kind of an infinite dimensional version of it, and from there we can possibly, right? Right, and that follows this fact that I've been studiously not erasing. Right, that comes from this fact. Right, this goes to 0 now. Right, that's the point here. This goes to 0 as n goes to infinity, thanks to the theorem, and so the L2 norm, this thing as n goes to infinity converges to the L2 norm. So it just follows from the theorem plus star. this thing, you notice, is actually the same thing as the little L2 norm of the sequence, right? So if we look at the sequence of Fourier coefficients, the little L2 norm of that is the same as the L2 norm, of the corresponding function, right? So in other words, there's isometry. There's isometry between these functions and these sequences. Okay, at the beginning of the next chapter, we'll give an example of a sequence. So the isometry is not onto. We'll give an example of a sequence that is in little L2 but doesn't correspond to a Riemann integrable function over here. Another important corollary, the Riemann-Lebesgue lemma. So what this says is that the Fourier coefficients go to 0 as n goes to infinity, right? If f is integrable, the Riemann coefficients go to 0. So the Fourier coefficients go to 0, and that's just because this thing converges, right? So you know that the coefficients must go to 0. I may be misremembering, but I think my advisor, who was a student of Stein, said that on his qualifying exam, Stein asked him, what can you say about the coefficients of of these things as if your function is if your function is integrable, what can you say about the coefficients? And my advisor, just sort of cheerfully said, yeah, the Riemann-Lebesgue lemma shows this sort of thing. And then Stein said, is that all? And then so the rest of the exam was him on the spot trying to derive results from this.
Oh my God.
So, yeah. Okay. Okay. Another result. Should we do it? Should we do it? I think I'm not going to do it. So there's another result. It's kind of cute, called the Polarized Parseval's lemma. So Polarized Parseval's lemma. Right, Parseval's lemma tells you that that you have this sort of result. Parseval's lemma tells you that you have this sort of result. You can use the so-called polarization identity to see that if you instead take two functions, right? Take two functions and look at the inner product, then that gives you the inner product on the L2 side. Okay, but I'll just let you guys do that because I rather want to get to the next thing. Okay, but I think Stein leaves it as an exercise to you. You can do it, or I have it in my notes if you want to see it. Okay. Okay. So yeah. Okay, so now let's go on to the next big result in this chapter, which is about pointwise convergence. So we return from L2 convergence to consider this considerations of pointwise convergence. And the result that we're going to go for is the following, that if f is integrable on the circle, and f is differentiable at a point, then in fact the Fourier series converges pointwise there. Okay. In the next chapter, we'll see an example of why differentiability doesn't why continuity doesn't suffice, right? So if you have continuity, then you don't you can create functions that are continuous, but whose Fourier series don't converge back to the function. In fact, there are people who do this, who go after this sort of result. Like, I think there's some, I forget, there's some result, I could be wrong, but there's some result along the line that, like, you can take any set of measure 0 and construct a Fourier series that diverges at, you can construct a continuous function whose Fourier series diverges at all those points. Yeah, so, yeah. Okay. Okay, well, let's go for this. You should be able to get it, I hope. Okay, so proof, right? So we want to show that we can make this thing small, right? We can make the difference between S and F at theta naught minus F at theta naught small. I want to show this can be made small. And what we do is we say, well, we're going to write this, right? So what is this? Right? This is just the convolution. Right? This is the convolution against the Dirichlet kernel. Convolution against the Dirichlet kernel. The Dirichlet kernel, as we know, is not a good kernel, but it has integral 1, right? It's got one of the properties of the Dirichlet kernel, of the good kernels, which allows us to do this. It has a sliding in property, so let's slide it in. Right, so we get f of theta naught minus t minus the f of theta naught of e sub n t dt. Right. Okay, we rewrite this as f of theta naught minus t minus f of theta naught over t times t dn t dt. Right, because we want to take advantage of the differentiability. Right, and so let's we let f of t be this, this thing, f of theta naught minus t minus f of theta naught over t when t is non-zero, and we let it be negative the derivative at theta naught when t equals 0. Okay, so some observations about this function. F is bounded near 0, right? As t goes to 0, right? This thing converges. This thing converges to this, and so we know that f is bounded near 0. Okay. Further, it's integrable on any. It's integrable away from the origin. So on the set t greater than delta, right? For any delta greater than 0. And then there's the fact that we're going to invoke something from the appendix that these two facts together ensure that f itself is integrable. So we're just going to pull a fact here. So this function here is integrable. Okay. Okay. So let's rewrite that as f of t derivative by kernel ut. Okay, so at this point, we're actually going to use the Riemann-Lebesgue lemma by recalling the closed form for the Dirichlet kernel. So we rewrite this as remember, the closed form of the Dirichlet kernel was this, right? Sine of n plus 1 over 2 t over sine of t over 2. Okay. So we use trigonometric identities to rewrite that as sine of nt cosine of t over 2 plus cosine nt sine of t over 2. Okay. Okay. Okay, and that basically does it for us because well, now we can rewrite this as we can realize this thing as Fourier coefficients, right? We can recognize this thing as Fourier coefficients, right? Because we have this integrable function times t times divided by sine of t over 2, and then we have this cosine t over 2 sine nt plus sine t over 2 cosine nt dt. Right? But each of these things, right? Each of these integrals, right? If we look at this thing right here, right? This is just the Fourier coefficient, right? These are Fourier coefficients of these Riemann integrable functions, right? So you've got, these Riemann. This thing here is a Riemann integrable function, and we're getting the Fourier we're getting basically a Fourier coefficient of it. So as n goes to infinity, that goes to 0, and similarly for the other guy. Yeah.
Even though for one of these arguments we're pairing, cosine over sine, the other we're pairing sine over sine. So they're different functions that we're taking coefficients of, but both must go to 0.
Exactly. Yeah. Exactly.
Interesting.
Yeah. So yeah. Thanks to the L2 convergence, we get the Riemann-Lebesgue lemma. We get the decay of the Fourier coefficients, and that allows us to get the pointwise convergence here. Yeah.
So for the third line where it says 1 over 2 pi equals the interval from negative pi to pi of f of theta minus t minus f of theta naught over t, are we sure it's defined at 0? I mean,
well, see, that's the thing here. So we make up this function, and we give it this value. We give it this value here.
Oh, okay.
Right?
So it's continuous. Okay. Or,
Yeah. At least it's integrable.
yeah.
Yeah. It's integrable. Yeah. Yeah, so I mean, this thing, as t goes to 0, this converges to a value. So we don't have to worry about the function becoming blowing up or something like that.
Okay, got it.
Okay. Okay, so that's it, right? We see that as n goes to infinity, this goes to 0, and so we have pointwise convergence of the Fourier series to the function at any point of differentiability. Okay, so that's nice. And yeah. Okay. Yeah. So that leads to this corollary called the localization principle. Riemann, which says that if f and g are integrable on the circle, and f and g are equal in the neighborhood of a point, theta naught, then the limit of the difference of the partial sums of the Fourier series is 0 as n goes to infinity. Right. And that is, of course, because f minus g is differentiable at theta naught, right? Because it's 0 in the neighborhood of theta naught, right? So being differentiable there means that the Fourier series converges to the function which is 0, right? So the Fourier series of the difference converges to 0, which means that the difference of the Fourier series converges to 0. Okay, and right. Right. So the point here is that that the convergence of the Fourier series at that point is determined by local behavior. Yeah, that's why it's called the localization principle. Okay. So next time. We're gonna go for this thing of where we construct a continuous function whose Fourier series diverges. Okay, so yeah, that should be fun. Okay.
All right, thank you, Papa.
No, thank you.
Thank you.